Hello. In this video, I'm going to derive the formula pi r squared for the area of a circle with radius r. Everybody knows this formula, and we've come to the point in the development of integral calculus where our toolbox holds now all of the tools that we need to derive this classical formula. The circle with radius r has an equation in Cartesian coordinates that goes x squared plus y squared equals r squared. And we can write this as the y equals the square root of r squared minus x squared. Now that square root sign actually is defined to mean the positive square root of r squared minus x squared. So this formula is valid on the top half of the circle. And to calculate the area, I'm going to calculate the area of 1/4 of the circle and then multiply by 4. So that means I'll be doing my integrals between 0 and r. So the integral that I'm interested in is the integral between 0 and r, the square root of r squared minus x squared dx, and then I multiply by 4. And what I hope is that at the end of this calculation, I'm going to discover that the value of that definite integral is pi r squared. In order to get to that conclusion, though, we're going to have to use almost everything that we've done in the development of integral calculus. And so this is a very good illustration of how all of those tools fit together to solve one interesting and really fundamental problem in the study of geometry. The first step is to know that how an area is related to an integral, and that's what we've set up here. Okay, step one in the solution of the integral is to do a substitution. So now you remember everything about doing substitutions. We'll let x equals r times u. R is a constant here, so it's just some number, and we don't have to worry about it as if it's varying. And so that means that dx will be r du. It's a definite integral, and so we'll change the limits. U is equal to 0 when x is 0, and u is equal to 1 when x is equal to r. So the substitution changes the integral to 4 times the integral from 0 to 1 of the square root of r squared minus r squared u squared r du. The r du comes from the dx. And now the r squareds can come out of the square root sign. Square root of r squared is r. We have an r from here, so altogether we get 4r squared integral from 0 to 1 of the square root of 1 minus u squared du. Now what I really hope is that that final integral here can be evaluated to come out to pi over 4, because that will give me the formula for the area of the circle as pi r squared. All right, step 2. We actually have to work on this integral. So we're going to do an integration by parts to get this integral. We'll take v equal the square root of 1 minus u squared, and we'll take du equal to du. Recall the integration by parts formula. It says that the integral of v du can be evaluated as the product uv minus the integral of u dv. So I need u and dv. If du is du, then in fact u is just u. That's fine. But for dv, we're going to have to take the derivative of v with respect to u. And so dv is minus 2u over 2 times the square root of 1 minus u squared du. So I've used the chain rule differentiation here. The derivative of the square root is 1 over 2 times the square root. Derivative of what's inside the square root is minus 2u. So it's a chain rule that's going on there in that derivative. If we now put all of that into the integration by parts formula, the integral we want which is the integral of 1 minus u squared du, is u square root of 1 minus u squared, so that's the uv, minus the integral of u dv, which is u minus 2u over 2 times the square root of 1 minus u squared du. Okay, so integration by parts has changed our integral into something new. It looks more complicated, but it actually now is easier to solve. In step 3 of the calculation, we're going to simplify the final term by adding and subtracting 1 and then breaking up the integral. The integral of the square root of 1 minus u squared du is equal to, from our integration by parts, u square root of 1 minus u squared minus an integral. And we can divide out the 2 to get just minus u squared and add and subtract 1 here. That won't change the integral. And we're going to then split apart this final integral right here after the u squared. So we'll get this is equal to u square root of 1 minus u squared minus the integral of 1 minus u squared over the square root of 1 minus u squared plus the integral of 1 over the square root of 1 minus u squared du. Now, why do we do that? Well, we do that because we now recognize this final integral as one of our standard integrals. One of the ones we just know. We know that the integral of 1 over the square root of 1 minus u squared du is the inverse sine function. It's inverse sine u plus a constant. So that means that we can actually evaluate that. We know how to handle that last integral. What about the one in front of it? Well, the integral of 1 minus u squared over the square root of 1 minus u squared is in the form of some expression divided by its own square root. So the numerator is the square of the denominator, and you just divide the numerator by the denominator and you get the integral of the square root of 1 minus u squared. So that's just simple algebra to show that those two integrals are equal. So if we put this all together, we have step 4. The integration by parts formula said the integral of 1 minus u square root of 1 minus u squared du equals u square root of 1 minus u squared minus the integral of the square root of 1 minus u squared du plus sine inverse u. So that's the arc sine from the last integral. The key thing to notice here is that the integral on the left appears on the right with a minus sign. So if you add this to both sides, you will get 2 times the square root of 1 minus u squared du. You can move this to the other side, and now we only have an integral on the left. So the integral of 1 minus u squared du is 1/2 the u square root of 1 minus u squared plus inverse sine u plus a constant. So we have now evaluated that integral that we set out, the indefinite integral that we set out to evaluate. This is the one where we were hoping it was going to be pi over 4 when we were done. Okay, so now let's actually solve the problem. The area at the very beginning we calculated was 4r squared, the integral from 0 to 1, square root of 1 minus u squared du equals 4r squared. Now we use this formula times 1/2 u square root of 1 minus u squared plus sine inverse u, and I evaluate that at 1 and subtract the value at 0. So now this is the value for the area of the circle. So let's evaluate that and see what we get. The first thing to note is that when you put 1 into u square root of 1 minus u squared, you get 0. If you put 0 into u square root of 1 minus u squared, you get 0. So this term in the antiderivative won't give us anything in the answer. It's going to be 0 in both times. So what we get is 4 times a half, or 2 r squared, and sine inverse of 1 minus sine inverse of 0, because the other term evaluates to 0 always. So sine inverse of 1, the angle with sine 1 is pi over 2 when we work in radians. The angle with sine 0 is 0. So we get 2 r squared pi over 2, which is pi r squared. And so now we have calculated that we have always been using the correct formula for the area of a circle. And I can assure you that in fact we have not done any circular reasoning, because you don't need the formula for the area of a circle to calculate the trig functions. Step 6 is check all the steps. Always check your work, always make sure you've done everything correctly. And as we wrap up this calculation, I want you to reflect on the following. To do this integral, it actually requires that you do a large number of things accurately and confidently. We first of all had to formulate this as the area problem as an integral. We then performed a substitution in a definite integral. We then had to carry out an integration by parts. We then had to correctly manage a bunch of algebra in order to simplify our integrals. Correctly manage all the plus and minus signs. We had to recognize a standard integral, the inverse sine function, but we had to be able to recognize standard integrals in order to know that they were under control. We had to manage somehow this recurrence of the target integral on the right-hand side. That's where we moved it over and then divided by 2. And then you have to be able to correctly evaluate the antiderivative when you get to the end. So all of these 8 steps are major skills that you will have developed as you worked on calculus. And this one calculation illustrates how we can bring all of these different skills to bear on a particular problem. This doesn't really show you how you would have gone about finding your way through all of this. I was leading you through the process of doing the calculation, but along the way you were exercising all of the skills that you've developed in doing calculus and algebra.